There is a battlefield smaller than the head of a pin, where the enemies are totally invisible, and the stakes are, well, life and death. And no, this isn't science fiction, it's the world of pathology. Today, we're going to explore how technology is giving doctors some incredible superpowers to fight these invisible battles and keep all of us healthy. So, it all starts with something you've probably heard of, a biopsy. A doctor takes a tiny little sample of tissue. But have you ever wondered what happens next? Well, that sample gets sent off to a pathologist. Think of them like a cellular Sherlock Holmes. Their entire job is to find clues hidden deep inside our cells. But how did they even start looking? All right, let's get into it. The whole field of pathology is really built around answering four huge questions about any disease. It's kind of like the ultimate diagnostic checklist. First up, what caused it? Was it a bacteria, a virus, something else entirely? Second, how did it develop? How did it move and spread inside the body? Third, what physical changes did it actually cause to the cells and tissues? And finally, what symptoms did all those changes lead to? As we're about to see, engineering gives us the tools to help answer every single one of these. Okay, so the first and, let's be honest, the most obvious challenge is just a problem of scale. The things that cause disease, the bacteria, the viruses, those rogue cells, they're hiding right under our noses, but they are just way too small for us to see. Yeah, this really puts the problem into perspective. With our own eyes, we operate in a world of centimeters, and maybe, if you've got really good vision, millimeters. But bacteria, they live in the world of micrometers. That's 1,000 times smaller. And viruses, they're down at the nanometer scale, which is 1,000 times smaller than that. So to see them, we can't just squint harder. We have to literally magnify their entire world up into ours. And that brings us to our first piece of incredible engineering, the microscope. It's not just a single tool, it's this perfectly integrated system. You've got the optical system, right? The lenses that do all the magnifying. Then you've got the illumination system to light everything up. And of course, the mechanical system, the stage and the focus knobs that let you navigate this tiny, tiny universe. So how do these lenses actually work? Well, it's really a battle between two principles of light. Our hero is refraction. That's the bending of light as it passes through the glass lens, and it's what creates that bigger, clearer image we need. But the enemy is reflection. That's when light just bounces off the surface of the lens, creating glare and washing out all the details we're trying so hard to see. Engineers fight this enemy with two main weapons, incredibly precise polishing and these special anti-reflective coatings, which are basically tiny transparent layers that coax the light through the lens instead of letting it bounce away. And this is a brilliant way to think about it. Not all microscopes are created equal. A standard optical microscope uses light, which has a pretty long wavelength. Think of it like a fishing net with wide holes. It's great for catching bigger fish, like cells and bacteria. But an electron microscope uses an electron beam, which has a super tiny wavelength. This is like a net with an incredibly fine mesh. It can catch the absolute smallest things, like viruses, revealing details the other net would completely miss. Now, looking through an eyepiece was for sure revolutionary, but it's got its limits. So the next huge leap in pathology meant we had to move the image from a piece of glass to a computer screen, basically from the analog world to the digital one. And this is where the slide scanner comes in. Honestly, the best way to think about it is just like one of those flatbed scanners you might have used for paper documents. A little light bar moves across the slide, capturing the image in these tiny strips or tiles. Then, some really powerful software stitches all those individual pieces together into one gigantic, high-resolution digital photograph of the entire tissue sample. So, we solved one problem, but that just created a new one. Now we have this absolutely enormous digital image, but how is a doctor supposed to analyze every single cell? The amount of data is just overwhelming. And this is where engineers started to train a whole new kind of eye, an artificial intelligence. Okay, so how on earth do you teach a computer to spot disease? Well, engineers focus on teaching it to recognize three main types of features. First are structural features. That's all about the physical stuff, like a cell's size, its shape, its thickness. Then there are molecular features, which look for chemical clues, like the amount of a certain protein. And finally, functional features, which analyze behavior, like how fast cells are spreading. By learning all these patterns, the AI can start to spot things that just don't look right. But how does an AI actually see this stuff? It doesn't see colors the way we do. At first, it just sees the image in literally thousands of shades of gray. Then, engineers give it a set of rules. They might tell it, okay, Any pixels in the darkest range of gray, say from 950 to 2024, that's a cell nucleus. Let's color those green. Then they'll say, any pixels in this middle range of gray represent another feature. We're going to color those blue. And by following all these rules, the AI transforms a flat grayscale image into a color-coded map, highlighting all the important features and just ignoring the background noise. It's pretty cool. So, this brings us to right now and the very near future, where all of this tech is really starting to come together. And the goal isn't to replace the human expert, but to give them the most powerful co-pilot you could possibly imagine. Just look at this evolution. It's wild. We went from a doctor squinting through an eyepiece, relying only on their own experience. Then came digital pathology, where they could see the image on a screen and use some basic tools. But now, with AI-powered pathology, the computer doesn't just show the image, it analyzes it, spitting out an automated report in seconds with super precise data on cell size, protein levels, you name it. It's a massive shift in both speed and detail. And this, right here, is the most crucial takeaway. This technology is designed to be an assistant. The AI can count millions of cells, it can measure tiny changes in proteins, and it can flag suspicious areas way faster than any human ever could. But the final diagnosis, that critical judgment call, that still rests with the experienced pathologist. The AI provides the data, the doctor provides the wisdom. So as we look ahead, the real question becomes this. By pairing the tireless, data-driven eye of an AI with the intuition and the expertise of a human doctor, are we on the verge of a totally new era in medicine? One where diseases are caught sooner, diagnosed more precisely, and treated more effectively than we ever thought possible? It's a future that's being built as we speak, one pixel at a time.